So uh, so this okay, so just to make sure that you guys just watch the video that you know the previous lecture I think I described like three simple quantum algorithms. So just to make sure that you need to first understand these three quantum algorithms so that you can understand this lecture. Because in this lecture, we are going to introduce so-called Shor's algorithm, which is the you can view this as the most important or the most it's basically the most important quantum algorithm in the history. Because simply speaking, before Shor's algorithm, right? The most famous quantum algorithm is this Simon's algorithm. So remember, so let me just recap, right? So the Simon's algorithm is simply speaking, you have some Boolean function, and then you are promised that there exists a secret x, let's say, which is non-zero vector, such that f of x and f of y is the same if and only if, say, x is y plus x. I mean, if you see the videos, that is. So this is supposed, and the goal for you is to find s. Right. As I proved in the in the previous lecture that for the best classical algorithm to find this s. Okay, so you can imagine that this is difficult. Right? Why this is difficult? Because this condition is saying that f is 2 to 1 function. So the goal for you is to find s, meaning that if you find x and y such that they are the same, then this condition will satisfy. Then basically x will be x plus 1. Right. The reason is that if you just add y, you get x plus y equals to y plus s. But we are working in the 0 and 1 universe, right? So there's no 2y, there's s. So intuitively, why this problem is hard because you're asking this function is 2 to 1. And why is problem hard? Because you need to find a pair. You need to find a pair such that they are the same. And the number of possible inputs is 2 to the n, right? So this is exponential large. Let's say n is 100. You get 2 to the 100 different inputs, and each guy is a perfect match. So the why this problem is hard because you need to find a perfect match. And I think I proved in the previous video that last week lectures that it's 2 to the best classical. You can prove that the best classical is the square root of 2 to the. So this is exponentially difficult. And for quantum, if you have checked the videos, that basically you can just run some quantum circuit, and then you will get some different. You will get some measurement. You will get some y1, y2, ym. These y are vectors, 0, 1, mb vectors, such that this y is all these yi are perpendicular to are normal to s. Okay, and the idea is that if you do such quantum algorithm for enough time, right, you will get bunch of yi and y1 up to ym such that they are all perpendicular to s. Then you can solve linear equation to find s. And the idea is that this only takes like square the times is basically linear equation. Maybe 10 in something. So it's like if you pick n to be 100, then for classical you need almost like 2 to the 50. And for quantum, maybe you just need like it's linear, so you need only 100 times. This is huge. So this is why these quantum algorithms are famous. This I think in 1992 or something. And then this is called Simon's algorithm. Okay, so actually the history is the following: is that Simons submitted this algorithm submits this algorithm to some conference, and then the people reject people reject this paper. And what and people think that quantum computing is just something because people think that this kind of question are mathematical question. So just someone which is like very, I mean they have plenty of time, so they sit at home and try to find some weird mathematical question that quantum can solve. So people just reject this paper. And one of the committee in one of the member in this committee is basically Peter Shor, which is uh I think I don't know what I think she's MIT professor, but at that time I think it's just some I think he's a member of the committee. But Peter Shor knows enough mathematics, so once he find this Simon's algorithm, he find that if he change this use more abstract mathematical way to build this Simon's algorithm, then actually one can build a quantum computer itself. So-called
So in this algorithm, m is smaller than n.
No, in this algorithm, n should be larger than n. Okay, yeah, okay, should yeah, much better than n. So that because f is 2 to 1, right? So this should be plenty of n to absorb. Because f is 2 to 1. So in order for this to be satisfied, your n at least need to be greater or to n or square.
Wait, but if you have so that if okay.
Yeah. So
the other way around, yeah.
Right, yeah. Oh, so in that time that Peter Shor will find some very very amazing application on solving the cryptographic system. So it's basically solving so-called RSA crypto algorithm. So that this become like then people is very amazing. So people start to try to build the quantum algorithm, basically due to this short spectrum. So I will try to explain this Shor's algorithm, right, in the detail. So just some recap. So just I want to say that before 21 centuries, there are two types of basically most famous quantum algorithms. The first one is this chapter 5, which I will try to as most I would say most complicated lecture. This semester is this one, and now is trivial 6. We will also explain. So these two are the main quantum algorithms before quantum logic. Okay, so basically, before Shor's algorithm, quantum computing is something interesting and funny math game, right? But there's no serious application. As for example, this Simon's algorithm. But before we start to talk about it, I just want to explain some classical cryptographic history. Right, so cryptography is something. Okay, I'm not expert, but so the idea for this cryptography is that someone want to send some message to the audience. So, but you don't want to just publish this message. So somehow you need to make a message to change this message. I think it's called the cipher. And after that, the people and so if Alice wants to send some message to Bob, they need to have some agreement. So that Alice will encrypt her message and then Bob will decrypt the message he received. So this is the idea. And I think the most famous one is this one. It is 2,000 years ago. Is that, for example, if I want to send the English, one easy way is that I just shift every letter by 3. So, for example, if I want to send ABC to someone, I just send DEF. I mean, this is stupid, but this is actually indeed in the history. And this one is easy to break, right? Because if you see something which is weird, you just try to shift it by 26 different different letters, and then you know, and then you say, oh, you know which it is if you understand enough English. Right? So this is the simple one. Right, so this is just very simple. And after like once several hundred years, then people know some like people invented different cryptographic systems. Okay. But simply speaking, there are not the modern one. So there are a few of them. And you can view that cryptography actually like change with cryptography and the computer algorithms they are like both they are like interchangeable with each other, because if you want to create some cryptography somehow you can design an algorithm. So actually there are a few different kind of cryptographic systems. So yeah, these are just some history. Okay, so the most important one is this RSA that I will explain here. Okay, so this is just the summary. So you start with very simple shifted, and then after the reason one is most famous one is RSA. So I will explain RSA, what RSA mean, and why on the algorithm will change, may change. Will make this RSA unsafe. So RSA is invented, I think it's in Stanford or MIT by three professors or three researchers. And they use some number theory. Okay, so I will explain the detail. Okay. So before we talking about RSA, I need to explain that there are like two main cryptographic systems nowadays. One which is called symmetric and asymmetric. So RSA is somehow a symmetric one. So I will explain what is it. But idea is that in order to give you in order to encrypt your message, right? If I want to send some message into someone, I need to encrypt it. So I need to use some key to encrypt. So the symmetric key meaning that if I want to send a message to someone, that guy and me use the same key. And then asymmetric meaning that they use different. And they say, oh, you don't understand it, but it's fine. That means so. For example, so this is the simplest one so-called one-time pad algorithm. Is that this is the simplest and most secure. For example, Alice and Bob, right? They share a secret key K, which is unknown to each. So you K is just a bit string. Okay. And for example, very simple, right? The encrypted message is that if Alice wants to send some message to N, so you N is a bit string, and 0, 1, 1, 1, 1, 1. And ciphertext is very simple. Just E equals to you just N X or K. So X or just E should be just change whatever it is. You know what I'm saying? For example, very simple. This is very simple. Just use similar as this Simon's algorithm instead. For example, if the message is the message is 1, 1, 1, 0, 0, 1, and then say the key is 0, 1, 1, 1, right? And you get this guy is encrypted best by just using the sum of these, just exclusive of, right? So this XOR. So just add just addition in Ma2, so it's 1, 1, 1, 2. Very simple. And the decryption is very simple. Just add the K. Just add K back, right? If you add K, K is 0, 1, 1, 1, right? So once you just do the sum in Ma2, so 1, 0, 1, 0, 0. And you get back. Yeah. Okay, so this is very trivial. It is very simple. So simple meaning that if Alice and Bob share K such that K which is so they know K, but no one knows K, then this method is completely safe. But there are some disadvantages is that for this one-time pad method, because and this is perfect safe, right? Because if learns nothing about the message. Let's say that's it. I mean, if you use k this k random, then there's no way that you can recover the message if you don't know k. But the idea is, but there the disadvantage, for example, it requires a truly random key, and the problem for this message is this key need to as long as the message. If I want to send a large message, I need a large key, and the key can be only used once. If I send a lot of message and then I use the same key, then why don't just try all the possible keys and then get the message back. It's similar as this shifting method, but now you have more possibilities. Okay, so this is indeed used. So practical limitation is that you need a trusted channel to exchange keys, and in practical for large or frequent communication because the keys run out frequently. And also one problem for this is that, for example, if there are a lot, for example, if we need to like talk to bank, right? So bank need to so for example, if all of us need to like talk to bank, then I use one key between me and the bank, and there another key. So you need a lot of keys. So this is an advantage. All right, but before we talk about this RSA, I need to do some elementary number theory. Okay. So very simple. I just go one by one. So the first one is the prime number. Everyone knows about it. Positive integer coordinate 1 that exactly true as this thing 1 dividers. Prime number, I think everyone knows. 3, 2, 3, 5, 7, 11. Okay. And we all know that there are infinite of primes. This is proved by OC in 300 BCE. I mean, everyone knows that there are infinite primes. And the proof is very simple. Suppose there are some finite primes. Suppose primes are finite. Then you just take a number n, which is just the product of all the primes, and plus 1, then you get another prime. Very simple. Okay. And there's called the fundamental theorem of arithmetic, say that every positive integer greater than 1 can be expressed as a product of prime numbers. And this factorization is unique up to the order of factors. For example, 30 is 2 times 3 times 5. This is fine. And the number which is not 1 is not prime number, is called composite number, which is a positive integer greater than 1, which is not a prime. And also there's an idea called prime, relatively prime, meaning that two positive integers are prime if their greatest common divisor is 1. So for example, 3 and 5 is prime, and 6 and 12 are not. These are simple. Okay. And greatest common divisor, I don't need to define. Basically, largest positive integer that divides both numbers without remainders. For example, we use GCD, right? Greatest common divisor. GCD for 13 and 12, 34 is 1 because they are prime. You can check. And GCD for 12 is 18 is 6. Okay. If you have any question, then you can ask. Oh, now everything becomes non-trivial. Okay, so we start the so-called Euler's theorem. So after 100 centuries, after like 1,000 years, he says that for any integer x, which is compared to the large number, let's say you pick any positive integer n, compared to n, there exists a number called the phi of n, such that x to the power phi of n divided by n is 1. Okay, so the equation so the way to read this equation meaning that x to the phi of n divided by n, the remainder is 1. This is the notation. This guy is very large, right? Some power, but when you divide n, the remaining is 1. This is called the Euler theorem. And notice that this phi of n is just so-called Euler torsion function. The definition is the number of integers less than n, they are relatively prime to n. Okay. And when n is p times q, when p q are primes, this phi of n is p minus 1 times q minus 1. Okay, so if you don't understand this, I will show you one example. Okay, this is also elementary number theory, but not so elementary. But I think maybe in some when you're at elementary school, there is this kind of exercise. So you know, so this theorem says that you fix on A, you fix on large number one number A, there exists some number such that for every number relatively prime to N or prime to N, this guy, this x to the 5n divided by n always the remainder is always that. Oh, you might say, oh, what are you? So right, so for example, let's say n could be 10. So this is like an example. And one can compute this 5n, right? Let me explain. So 5n, you say by definition, it says that this is the number of integer less than n that are relatively prime to n. So how many of them? The number less than 10, which is relatively prior to 10, is basically 1, right? 3, 7, 8, 9. Because 2 is not prior to 10, prior to 10. 4 is not, 6 is not, 8 is not, 5 is not, right? So it's 4. What? Now let's say I take any number, let's say 3. So for example, 1 to the power 4, right? Is 1, right? Which is not 10. Because 1 divided by 10 is remainder is 1. And then 3 to the 4th is 81, right? So it's mod 10 is also 1 mod. Good. Now you can compute 7 to the 4th. It's digitally computed. But let's say I can do this. I can just compute a square. So I get 49. Right, it's not 10. But 49 is just the remainder is 9, right? But I can change, I can use -1. But -1 squared. 1. Okay, and for 9 to the 4th, just very do -1 to the 4th of 10. That's 1 mod. So this is just an example to show this theory. Okay, by the way, the proof is somehow not so difficult. I will try to explain it, but okay. And when n is p times q, where p2 are primes, the phi of n has a relatively simple formula p minus 1, 2 minus 1. For example, this is 2 times 5, right? Hey, 2 times 5. So this is 2 minus 1, 5 minus 1.
And this also works if you have 3 primes, right?
Sure. Definitely. So this is here. Yeah, you have basically it's true for you have arbitrary number of primes. Yeah, so for example, let me explain. So if your n is let's say I read P1 A1, P2 A2, and let's say Pn AM, then this phi of n is just n times 1 minus 1, 1 minus 1 divided by P2, 1 minus 1 divided by P. Okay, so why is it okay? So for example, if you so this is general formula, but let's say if n is p times q, then phi of n will be just n times 1 minus 1 divided by p, 1 minus 1 divided by q. So it's just p minus 1, 2 minus 2. This is the general form. Okay, so the intuition why this is true is that the intuition is true. Let's say if you random pick a number, the probability for this integer to be even is half. Right? It's very simple. And similarly, if you pick a number which is a multiple of 3, the probability is 1/3. So if I randomly pick a number which is not a because you need this number counts the number of integer which is compared to n. So it should be compared to p and compared to q. It should not right. So if you pick any number less than n, this number, in order for this number to be relatively prime n, meaning that this number is not a multiple of p, also not a multiple of q. And the probability for this guy to be not the multiple of p is just 1 minus p. So we get 1 minus 1 minus q. So this is the proof. Yeah. Basically, the proof is just this. Elementary algebra. So for you, yeah, okay, is somehow an exercise. Okay. So let me just skip a little bit. Okay, so if you believe it, in order to prove this, you somehow require some amount of work. Let's say you believe this is true. And now I can use this RSA encryption. I can explain this encryption method. Oh my god, very crazy. So the next right here. Okay, so let's say Bob wants this. So let's say for the first, Bob choose the two large prime numbers p and q. Which is very okay. So there are some details. So the detail is that there exists an algorithm, classical algorithm, which you can generate large prime. You can check whether a given large number is prime. If efficient, this is done in past 20 years ago. So it's very simple. It's not so simple, but there is a way to give you the two prime, which is very large. Okay. So just pick a very large two primes, and then you can multiple of them. So this is simple. Just execute again. Now Bob choose a number called e, which is less than n, and find d such that x to the power ed is x not n. So so one question is that why is d this? Okay, I will explain later. But let's suppose d is this. So Bob choose some e, and there is a d such that x to the ed is x fine. Alright, so now Bob has a so-called private key will be d. So private key meaning that you cannot share this key to others. This is called private. And then there's a public key will be the pair n and e. So this n and e are exposure to everyone and anyone. So anyone can see this n. Right. It's somehow so I try to maybe draw. This guy is very busy. Right. Yeah, but the technical, I mean, the difficulty of this lecture is somehow like much difficult. So let's say Bob, right? So Bob has let's say your Bob. So Bob know n and d and e, right? And the d is his private key, and Bob will share n and e to the outside. So let's say this is Alice. Right, so Alice knows n and e. So now in the encryption is that suppose there is a message x. So don't use anything for all x. So let's say Alice takes some message x, and then just do the encryption. So encryption is just x to the power e by n. Okay, so this is a separate text. Just x to the power e by n. So just if Alice wants to send x, she just send x to the power e and by. As long as x to the power e may be extremely large, right? But we just do not. We just take the remainder of this method. Okay. Then it's going to be y. And so Bob get y, right? So the idea is that Bob just do another power to the d. Bob just take x to the e to the d. So it's y to the d and by n. Then by definition, you get x to the e by n. Then for all x, this is true. So Bob will cover x. So simply speaking, this is y, and then above just do y to the d. Because this is x to the e to the d by n. Okay, yeah.
So somehow Bob has an easy way to find E and D as long as E is not yet fixed. And if E is fixed, then it's hard to find D.
No. So once Bob choose E, once E is fixed, then there is an easy way to find D.
Ah, okay, but then wait, but in that case, the outside world knows N and E.
Yeah, but
so they can try to find the D as well. And then also easily find it.
Yeah, so and I will explain why this is hard. I will explain why the idea is that Bob not only know n but know the factor of n.
Okay, yes.
So this is the key. Yeah, it's
that's
not,
right.
yeah, I will explain in detail. Yeah, this is the trick. Okay, so also there are some detail. Okay, so the first detail is that how to why d is this. Why there is always it is a d such that e times d is x by n. This is the first question we need to answer. Okay, so this is the key. This is the so let me explain here. Okay, so one component which is probably you don't know, but this is yeah, people already know in like 1,000 years ago. This is the famous algorithm. Basically, this theory says that if you give me two numbers which are proprietary to each other, you can always find x and y such that ax minus by is 1. Good. This is, for example, 7 and 3 are proprietary, so you can find 7 minus 3 times 1 times 2 is 1. Everyone knows. This is pretty high school math. You can okay. Everyone knows about nice. Okay. I mean, if you don't know, you can check Wikipedia. The proof is this is basically definition. Yeah. Okay. So now so we can explain here. So in order for key generation, Bob pick large P and Q, right? So Bob knows N is P minus T times Q, and Bob also knows 5N because by the there's a formula. So Bob knows all these numbers, and Bob can choose E such that GCD E and 5N is 1. Because Bob knows 5N, right? And 5N only has 2. 5N may have more prime factor, but very simple to choose this. Because GCD is easy to compute. If I give you two very large numbers, you can very easily compute with still very small divided. It's very simple. So Bob can find the E. Bob just pick E whatever E such that this is true. Then by this previous algorithm, Bob can find D times E equals 1 not by A1. Right? Remember this algorithm. Remember what I'm saying? Because E and D, E and 5N, their GCD is 1. So let's say there exists, let's say D and F, such that DE minus F by N is 1 by the previous algorithm. So that means that if you divide this equation by 5N, basically you say that DE is 1 not 5. Good. Because this is multiple of 5N. So if you divide 5N, this guy vanishes. You got to remember this one.
Oh, that's the proof.
Yeah, it's a proof.
Okay, nice. Right.
So if we have, so I prove D is this. Okay. I did the proof. Since D is 1 plus C by N, then we have. Oh, sorry. So now, once the teacher is right. So once this formula is true, then I need to check that x to the DE is x for each x. And then we just get x to the DE, which is x to the 1 plus C times phi N, because I say that DE equals 1 plus C by N for some C. Now it's become x times x to the phi N to the C. Now up to now. Finally, we have the Euler's theorem. Euler's theorem, I just do some demos and convince you that any number x to the phi of N is 1. mod n, right? So it's 1 to the c, mod n, which is 1 is s. So we cover this. So this ensures the original message x is recovered after the decryption. The proof. So proof basically has these OCD algorithms and also this formula theory. So combine these two number theory results, then you get this RSA approach. So if you find this is hard to understand, you just need some number theory background. And yeah, I mean, probably it's from high school or something. The proof of all your theory is not high school. Yeah, it's not, but it's not so difficult. You can check. If you don't understand, I can prove it. But this is the idea. Okay, so this proves these RSA indeed work, right, by these two theorems. Okay, so these are some trivial example. I think I don't need to explain. For example, let's say Bob, 10 equals 3 and 2 equals 11. Just compute this n, which is 33, and 5n just 20. And then just choose some e such that e is less than 5. Yeah, just factor that e and 5 are compared. Let's say e is 7. 7 and 20 are okay. And then just find a value b such that this equation is true. So one solution is equal to 3 because 7 times 3 is 21. 21 if you divide 21 by 20, you get a remainder of 1. So the public key will be public key is everyone can see, right? It's basically 7 is 33. And public key is 3 and 33. This is okay. And for example, let's say message is 2. Then the ciphertext is just 2 to the power 7 divided by 33, which is 29. And when Bob receives 29, you just do the 29 to the power 3 divided by 33 gets the 3. So this is the famous RSA algorithm, which is nowadays, I believe it's nowadays still using in the real system, like computer or what, or for example, you want to use your credit card. But I use that real application. These prime P and Q are like 1,000 bits long, like the 1,000 bit term. So it's very large. Cannot be just twice. So number of n is like 2,000 bits long. Okay. So we believe that people believe that RSA this method is safe. And there are state of the art is that for example, so let me explain. Let's see. Okay, so this shows some detail that why greatest common divisor is easy to compute. There is an algorithm that is easy to compute. Okay, so one obvious thing is that so if you believe RSA is safe, then you need to believe that I give you a 1,000 bit long number, finding its prime factor is hard. For example, if you know because we know that because the public key is n and e. So if I can factor n in terms of into p and q, then I can get 5n. If I know 5n, then I know d and I know 5n, then I can run this algorithm to find d. Then which is not safe, right? So if RSA is safe, if and only if factoring is hard, meaning that factoring cannot be done in classical using classical computer, cannot be done efficiently. So for example, I think the largest RNA number factor is 829 bits. It's almost like 250 decimal digits, and it requires like 1,000 CPU years to just run. So nowadays, if you use a 1,000 bit long like RSA, then should be safe because of that. So yeah, so this is the P density. P density is less than 300 bits, and we factor in power using the PC. And for 500 bits, it's already I think it's 90. Yeah, this is not like 1 year ago. Now it's low in a week. And then nowadays we use 1,000 bits or 2,000 bits for us. Okay, so I think everyone knows. So that means that so the take-home message is that RSA this encryption method is safe, if and only if factoring is hard. Okay. These are just some detail that if you want to check, this is just an algorithm, just a simple PowerPoint that I try to explain why finding equations compact divisor is easy. I think everyone knows about it. If you want to find equations compact divisor, just keep doing division. Okay. So the idea is that okay, but what's the relation between RSA and quantum computation? This is why we are here. So let me define factoring. Simple, right? Given a composite number, we want to find a p and q such that n is p2 p times q if there exists. I mean, if a is prime, then you can check it, right? But yeah, but the problem is you need to find some prime factor. Okay, so these are so-called search version because you need to find the prime factor. There's a so-called decision version. Decision version meaning that if you two numbers and the n, thus there exists a non-trivial factor of n less than n. This is the same as factor, but I change it to the decision version. This decision version is in MP because if I give you the prime factor, you can easily check it. This is definition of MP. Right? Definition of MP is that if someone give you a certificate, then you can check. If I give you a prime factor, you can just do a division. It's very simple. You just do a division. And one topic on trivial is that it's also in OMP, meaning that there's a witness if the answer is no. What's a witness? So do we know what I'm saying? So this is the definition. Is that I give you two numbers. I'm asking whether there's a non-trivial vector of n less than n. One trivial result is that this is in MP because if the answer is yes, then I just give you the prime factor to the division. And why this is for MP? Because if the answer is no, we already know that every positive integer has a prime factorization. So this prime factorization will be a certificate. You just check whether there exists a prime. If you see, you can easily check whether it exists a prime. You just look around this prime factorization. Then you can check. So factoring is a spatial problem. Factoring is not a general NP complete question, or we believe factoring is not NP complete question because factoring is the intersection of this MP and OMP. This is not a general characteristic of NP complete question.
What was the definition of MP?
Oh, NP complete is that all the problem can be reduced to such question. So you can use the most difficult problem in NP. The one canonical example is that I give you a Boolean circuit, and then you check whether there exists assignment such that it's compute one. So what I'm saying is that if I give you a Boolean function, and you need to tell me where there exists x such that x equals to 1. So this problem is NP complete. It's most difficult problem in NP. Right? This is the definition. So what I'm saying is that in this let's call it set, which is a satisfiable assignment. Or satisfiable problem. So this definition, this problem is that I give you a Boolean function, and you want to tell me where there exists x such that the output 1.
Yeah.
So obviously this problem is in NP. Because that if the answer is yes, you just give me x.
Yes.
That's throwing that answer. But what about but whether this problem is in NP, we don't know. Because if the problem is no, where is the certificate? It seems that there's no easy way to convince. If I want to convince you that this circuit has a correct, if I want to convince you this circuit has an assignment such as output 1, I just give you that assignment, and you can compute by yourself.
Yeah.
But if this circuit has no assignment to make it 1, how can I convince you?
Give you all the outputs.
No, I mean, but I cannot. But there are exponential outputs, right? So I cannot just run one by one and tell, and you just. I cannot just run by one, but tell you.
So what is the precise definition? Because of course it takes a lot of time. But
the precise definition is that this to check whether the answer you can basically definition the precise definition is that you only have polynomial time.
Oh, okay.
Right. So this is the idea. So
and this is exponential.
Yeah, this is exponential.
Yeah.
As this way. So so this is why factoring, but factoring is different, but the characteristic of factoring is different from this, right? Because if the answer is not true, you still have this prime factorization. If I give you the prime factorization of this number, then you just check each prime. You just check this whether there is a prime which is less than n.
Mhm.
So that means that factoring is not just in NP but also in co-NP.
Yes. So you said exponential time for every dimension of the input, or
Exponential time meaning exponential time with
or I mean you said it is polynomial time, but on what?
On the number of the size of the input.
So the dimension.
Yeah, so if the size of the input is n, 2 to the n is not enough. Only polynomial. Yeah. So we believe factoring is not NP complete. Because factoring is not it looks like this satisfiable problem is harder than factoring. But it's fine. Just okay. So the best algorithm, a classical algorithm we know is that given n bit number. Oh, by the way, so when we talk about number theory, we always count the number of inputs as a number of bits. Okay, so if I give you n bit number, you can use n is like close to 2 to the n.
So is NP complete so a problem that needs higher than polynomial time in the input dimension?
No, this is the famous unknown problem with P versus N. Yeah, the problem is we don't know. The problem is most of people believe what you're saying is true, but they cannot prove it.
Oh.
Yeah, so this is famous P versus NP. This is famous P versus NP question, where P is equal to NP. If P is different from NP, then what you're saying is true. Yeah. If P is the same as NP, then there exists a polynomial time algorithm to solve this problem and factor it. This is what we don't know.
Okay, so what does the N stand for in NP?
Non-deterministic polynomial. Non-deterministic. Okay, so the most best algorithm we know is that if I give you an NP number, then it requires that O to the equal 2 to the n to the 1/3 for classical computer. But this is still exponential. It's not 2 to the n, but 2 to the n to the 1/3. Still smaller than 2 to the n, but still not a polynomial. So this is the best algorithm we know. Okay, so I have a dumb question. Why factor is not why factoring is hard? If someone gives me a number, why I just try each prime smaller? I just do a division. Why is it right? Yeah. Dumb question. Why factoring is hard? Why I try why? I just try each prime number less than n. So if you think a little bit, if this method fail, that means that the number of prime less than n is huge. If the number of prime less than n is very small, then I can just try one by one. Then I get classical algorithm. I get very efficient algorithm. So this means that the number of primes smaller than n will be huge.
It's a problem that there are. I mean, it is still of course order n.
Yeah, but is it so obvious? Yes,
you have to do n division, which is
is it? Yeah, so this is so-called prime number theorem. This is, or you can view this why intuition. This is my intuition why factoring is hard. An answer is called prime number theorem. This is a very difficult theorem. That Gauss conjectured this is in 200 years ago, and proved by proved you need to using complex analysis, and also Riemann connected Riemann. So basically, simply speaking, that the number of primes less than x is order x divided by log x. So this is called prime number theorem. This is some analytic number theorem, which is like very difficult to prove. I mean, I can prove this, but I take us 3 hours or maybe 20 hours if you solve in interview. And this also connects to Riemann. They will connect the called Riemann hypothesis. If I have time, it's fine. But proof will require more than 10 hours. So idea is that, so what it's saying is that you can see this part. So what it's saying is that the number of primes less than x is order x divided by log x. So simple thing is very large. For example, let's say if you give me 1,000-digit number, let's say you give me a number which is close to 2 to the this 1,000 digits, then the number of prime less than n is almost 2 to the 1,000, just divide by log of 2 to the 1,000. So this is still exponential large, very large, because you just divide by some number of this, just divide by 1,000.
Yeah.
So the number of primes are very you can say, oh, the price should be sparser. Because the gap between price will be large, will increase. But the number of price below x is still it's just x divided by log x. And it is very difficult to prove. In order to prove it, you need to know some analytic number theory techniques to control the number of price tensor to the x. Yeah, and these are some okay, actually I made 12 hours YouTube videos in like 4 years ago. Unfortunately in Mandarin I try to explain the proof. The proof is just maybe 10 hours. If the proof of prime is then hard. Yeah. Okay, so and there's an idea. So basically, if you know some mathematics, some math, one most famous conjecture is the Riemann hypothesis. So Riemann hypothesis is just one way that I understand is this conjecture try to control the error of this number. Basically, the Riemann hypothesis try to control the subleading order of this one. So we need to Okay. So theorem, I think I explained before. Actually, it's not safe if factoring is easy. Okay. And the reason is very simple because if I know n, if I can factor in terms of P of Q, then I get 5 of n. So as I said, the class non-classical algorithm takes about 2 to the n to the 1/3. So there has been considerable work devoted to finding a good factor algorithm because if you can factor, then you can break RSA. And the reason, as I said, if you get n, then you can know the P and Q, then you can compute 5 of P and Q, and then this the algorithm will give you D n from E. So this is why, yeah, this is RSA. All right, conclusion RSA safe if only factoring n bit integers require more than polynomial time in n. Oh, so this I think now like 20 years ago that Peter already knows about this. This is okay. So now we will need to talk about a problem called period finding. Okay, so now I need to explain why quantum computer is and very RSA. So why Peter Shor is famous because he knows enough number theory. So you know that there's a problem called period finding. If you can solve this period finding, then you can do the factoring. This is the number theory number theory is already known at that time. So let me explain why period finding. A periodic finding is simple. I give you a periodic function. Let's say from integer to integer, some periodic function. If you have some period, there's an R that does not otherwise repeat value. Let's say so big R is the smallest integer, such as fa plus R equals to fa, and fa divided by fp unless p minus a is a multiple of R. And the goal for you is to find R.
So, but it's not necessarily that fa plus R is fa for all a. Or it is.
I mean, yeah, I need fa plus R is equal to f for a for all a.
For all a.
Yeah, for a. And then the goal for you is to find the period. So this is the definition, so you need to find the period. Oh, okay, so we just skip. Okay. Okay. So this is a theorem that Peter Shor knows, or the number series already know that if you can solve period finding for large, if I give you a function where period is exponential large, but if somehow you have some amazing way or some weird way you can find a period, then you can do the factoring. And this is somehow like weird, but I will try to finish. Okay, so claims that factoring reduces to finding the period of a function. Let's say you pick A, you pick X, you pick some X, and you define a function called X to the A by N for arbitrary X. So first thing I want to say is that this function, this X to the A is a period function. Why? Question. So the question is that X to the A, as I define this. So I fix X. I view this as a function of A, right? So I define, so f of xa is X to the A by N. This guy is a period function. Wow. Because I know there's a.
Because if the greatest common divisor of X and N. Oh wait.
Why this is? I mean, for example, if you do X to the A and keep dividing by N, once you touch one, then become period.
Yeah.
Yeah, but simply speaking, that since I know that I already know that X to the 5, I have this only the theorem.
Mm-hmm.
For every X. So that means that if I keep multiple of X, I start with X squared. Once I touch X to the 5 of N, they always have 1. So that means that this guy is a period function. The order of R is a factor of 5 of N. Oh, the order. Or maybe, for example, I use this standard example, right? Let's say you pick, let's say previous example N to be 10, right? You take 3, you got square, this is 9. You got 27 divided by 10 is the remainder 7. Then you get 3 times 7, which is 21. Then you get back to 1, you get 3. So if you round this, you get 3, 9, 7, 1, 3, 9, 7, 1. You get a period function, and the period is 4.
Mm-hmm.
As this. By the way, this result just tell you that this result tells you that once you do up to 5n, mod n, you get 1. But this does not. But this does not tell. This does not just tell you that. This does not tell you that the order is 5n. The order just a factor of 5n. Because this theorem just tells you that once you hit 5n, then you must go back to 1. But maybe you get to 1 earlier. Yeah. So this is why finding periods is non-trivial.
Like if X is 1.
Yeah. Yeah. So different number has different X, has different order, has different period.
For X is B, I guess. For X.
Yeah.
And
so,
all the other numbers
has a period. Yeah, has a different period. So okay. So yeah, this is oh, so now you believe it's a period function. Okay, so the technical detail is that okay. So once you find a period, then you can do the factor. This is a little bit non-trivial. Okay, so let me just tell you why this is possible. So right, so. So let's say I give you X, right? And suppose there exists a way that you can find a period. So you find R. it is some this is some real way. Let's say you get some real way, you can find R, then you get x to the R, which is 1 mod n. Okay, so modulo two condition, one condition that suppose R is even. Let's say suppose. Just for simplicity, suppose R is even, which is in this case. Suppose R is even, then this equation tells you that x to the R minus 1 is multiple of n, right? So n, so because x to the R, yeah, x to the R minus 1 is multiple of n. And because R is even, right? So I can write x divided R divided by 2 minus 1 times x to the R divided by 2 plus 1. This guy's this. And it's okay, but notice that n is only 2 prime factor, right? It's a p and q. So if this guy is a multiple of p and q, that means that either there are 4 cases. Either p is in here, or q is in here or here. But you know, because n is because this guy, right? This guy is a multiple of n. So that means that this guy is multiple of p and multiple of q. And so there are 4 cases, right? Either PQ goes in the same here, or PQ goes in here, or P goes here, Q goes here. Okay. So there are four cases. So let's say so one case is that P and Q goes here. They are all goes to the first. My claim is that this is impossible. Why? Because if this is true, that means that x R divided by 2 is 1 mod n. Because this meaning that x to R divided by minus 1 is multiple of n. But this violated condition is R is the smallest number. This is true. R is the order, right? So this is impossible. Okay, so then there's a case that maybe P is in x to the R minus 1. And the Q is in x to the R. Or vice versa. Maybe it's right. But if these are 2 cases, then we get a factory, because I can just compute the greatest common divisor of p, and I can just compute the greatest common divisor of n, and the x to the R divided by 2 minus 1. Because now this guy P falls into this, and then P and Q falls into this, but Q does not belong to this, so you get P. So that means, and so in this case, then you get P. In this case, you get Q, and then you get Q, you get P. So yeah, so in this case, that if P falls into this and Q falls into this, and you just compute the GCD of this guy and this guy, you get P. Okay, so there are so the final case is that there may be such that n belong such that P and Q both belong to this guy. And in this case, you cannot get anything, because they fall into this. Okay, so there are 2 conditions. If R is even, and the second condition is the GCD of so condition, so meaning that you need to this cannot happen, and it's easy to check whether this happened or not. You just take this, compute GCD with n and this, then you get n. Or simply speaking, if P and Q both fall into this, then you compute GCD of this guy and this guy, you get 1, then you get nothing. Okay. So modulo these 2 conditions, if R is even and the first case does not happen, then you get factored. Then you get factored. Okay, maybe it's a little bit. Let me use one example. For example, let's say n is 10. I take x to be 3.
So Why can't we just so in the very first step where we find the r?
Yes, yeah.
Why can't we choose the x such that the greatest common divisor between x and n is 1, and then
you can.
And then we say r is equal to 5n. Is that always true?
No, because r needs to be the smallest one. I mean otherwise that you cannot skip the first case.
So it is not in general true, even if the greatest common divisor. Oh wait, because and then x
Yeah.
is 1 would also satisfy.
Yeah.
Okay, so that's true. Because otherwise, if you know phi n and you know and then you can go.
So the problem is for this. Okay, so one option is that you know n but you don't know phi n.
Yeah.
Because compute phi of n is the same as you know p and q.
Yeah.
Right.
Exactly.
Right. So you only know n but you don't know why. No, you don't know phi of n. You don't have massive. Because if you know n and phi of n, right? Okay, so let me explain. So if I know n is p and q, I don't know q, but I know n can be written as p and q, then phi n is I know that it's p minus 1 and p minus 1. Right? Suppose I know n and phi of n, then I have two equations.
Yeah.
So I can solve a quadratic equation in 5p.
Yeah.
So knowing phi of n is the same as factoring, as Harris factoring.
And is it true that if I have such a number n, then I can find an x that is between 1 and n such that its period is actually 5 n?
This is not true for general n.
Okay.
Yeah.
I mean, it wouldn't necessarily help maybe because we still need to do order of n then. But if that were true theoretically, then we could do all the x, and then we know that one of the periods is going to be 5 n.
This is the problem is that this is not true. There is a number. I think this is called the primitive roots for the number. Okay, so for the so for the given n, x is called the primitive roots of n if the order of x is 5n. And
not every number.
Not every number. I think this is proved by Gauss. I think it's. I guess it's some prime power, 2 times prime power, or whatever. I think you can check. You can use computer. You can check it. I guess n equals to 21 has no primitive roots. This is called Gauss primitive roots theorem. This is very number theoretical. Gauss primitive roots theorem. You can check it.
I guess it would surely be helpful if every number.
Yeah, the problem is no. So Gauss, this is a difficult question. I think Gauss proved that there exists. I think it's prime power and prime. Oh, yeah. I think I think one example. For example, you can choose x n equals to 8. So what is 5? 1, 3, 5, 7, 4, right?
Yeah.
Okay, so I only care about 1, 3, 5, 7. Okay, so now you can see 1 squared is 1, and the 3 squared divided by 8 is already 1.
Yeah.
And the 5 squared is 25 divided by 8 is already 1. And the 7 squared is 45 divided by 1. Right? So all of these guys order 2, but the 5 is 4.
Yeah.
So there's no x such that. Yeah. I think this because you told me that. I just remind me this example. So this is called Gauss primitive theorem. To prove this required. I mean, I post some videos on this. You can try to prove. I think it's several hours. You can prove there exists. You can prove that only particular case of n has the primitive roots. Okay. So for example, n equals to 5, we don't have primitive roots. The phi of n is 4, but every number has order 2.
Yeah.
Let me go back to this guy. Right? So for example, n equals to 10 and x equals to 3. Right? So I know the order is 4. Because 3 to the 4 is 1 mod. Okay? So I can use this algorithm. So I just compute the GCD of 10 and 3 square. Yeah, right. Right. I equals 4. Oh, maybe I change it. Sorry, this number. Let's say I choose n to be what? Why this example is number? Because 10 is, I already know 10 is an even number, so I don't need to. So for example, I choose n to be 5. Let's say x to be 2. Then the order will be what? 2, 4, 8, 16, right? So it's and so I can compute this. I compute the GCD where 2 to the 4 divided by 2 plus 1 with 15. And I can compute the GCD of 2 to the 4 divided by 2 minus 1 and then with 15. Then this is 5 and 15. Right? So this is 5. And this is 3 with 15, which is 3. And so this is just an example of factor. Right. So to explain this example, so let's say n is 15, you pick x equals to 2, then order is 4, because 2, 4, 8, 16, 16 divided by 15, the remainder is 1, so order is 2. And you just compute the greatest common divisor of 2 to the 4 divided by 2 plus 1, which in this case 5. 5 and 15 is 5. And then this one is a 2 to the 4 divided by 2 minus 1, which is 3. 3, 15 is 3. So you do a factor, so factor success. Because 15 is just 5 times 3. So this is one example. Okay, so hopefully this explains. So this explains period finding. So this explains if you can solve period finding, then you can factor. Because you can run this algorithm. This is done by, I think everyone, I think at database, there's number theorists already knows about this. So simply speaking, that so this is a Shor's algorithm. So Shor's algorithm can be used as just a mix of classical algorithm and functions. So we pick a random A, where A is less from 1 to n, and such that GCD AN is 1. If this one fails, then you already know to find the factor. So you can, so most of A will success. Will have no prime factor with. And so this is why quantum computer is powerful, because quantum can let you find order R. And R is R, you need to retry. Otherwise, then you compute A to R divided by 2 minus 1 or Q A to R divided by plus 1. And you compute the GCD with these two numbers as this. And then if you find a non-trivial factor, then you can check and return non-trivial factor. And the key math is this. And so I will explain the detail, but margin of these two conditions that I think one can show that the success of this algorithm is greater than 40%. So if you fail, then you just do it again. Then you have you just do it 10 times, then you get 99% is your success. So most of the mystery of this quantum, or most of the mystery of this Shor's algorithm is how can you use a quantum computer to find this order R particle. Oh, so I will explain so we just take a minute break. Yeah.